Hello, physicists, and welcome to the unit on magnetism. Very short unit, no formulas, just a few concepts. I hope you watched the two videos from Paul Anderson on Boseman physics. We're just going to continue on. This is all in his video about the domains and how something becomes magnetized. The interesting thing we're going to see here is that all magnets are dipoles, which means they have a north and south pole, and there's no such thing as a monopole. And magnetic field lines are called magnetic flux lines, and they're represented by these lines here. And the big thing here, the really big thing that you have to know, is that the direction of a magnetic field right here, the direction of a magnetic field is determined with a compass. So a compass, you might remember, is just a little case with a needle in there, and the needle has an arrow. The arrow is always north. It's a magnet, and the other end is always south. It's free to float on a pivot, and sometimes there's liquids in there. So if we ever come back, I'll show you some compasses that I have. Maybe you've used your own before. So to determine the direction of a magnetic field, you use a compass. And remember, the north end of the compass points in the direction of the magnetic field. The compass does not point north. It points in the direction of a magnetic field. You'll find out that that's a very important difference there coming up soon. Okay, so let's get right on to the samples here. And let's see, first one here. Maybe I'll make this a little bigger. There we go. So basically, in the first one, we're just going to go ahead and see if we can draw the domains. Actually, the poles first, just pretty simple. So it doesn't really matter. I'll start here with north. So if that's north, then this is south. Dipole. All magnets are dipole. So now we're going to break magnet number one into these pieces, and we're going to see what happens here. And we could test this. And so this would be north and south, and these become little magnets. And notice south to north, north, and south, and then north. So these become 1, 2, 3, 4 separate magnets with their separate dipoles, no monopoles. There's a way to test a magnet. You can't test it with something magnetic. You have to test it with another magnet. So just like in electricity, opposites attract, like repel. So now we're going to break that magnet lengthwise here. So this would be north, this would be north, this would be south, and this would be south. And what would happen here is the actual magnet would be repelling itself, because these would repel each other here. So north would repel north, south would repel south. Okay, so let's see here. Did I get this right? North, south, north. Okay, what about the flux lines here? So now we're going to take a look at how we actually can draw the flux lines, and there's a simple rule here. Well, I guess we're going to have to erase this previous stuff because it won't follow me. So diagramming flux lines are pretty easy. We're going to take and look at the actual poles first. So let's just go ahead here and make these make this again north and south. And so again, you would just always put a compass in there. Put a compass wherever you want. So wherever I put a compass, these are compasses. They're going to tell us the direction of the magnetic field. But we have to remember, north repels north. So the north needle would be repelled here. The north needle would be repelled here. The north needle would be attracted, opposites attract, and this north would be repelled there. So this would give us the direction of the flux lines when you connect them. The flux lines would be as such. So these are the flux lines, and the arrows are very important. You need to tell the direction of the flux lines. So magnetic flux units are actually named after Nikola Tesla, so they're called Teslas. Magnetic flux density is Tesla. Okay, so over here, if we have this compass right here, and we put north and south, we kind of did this already, but the compass now, you should be able to tell what direction it'll point. So this one would be repelled, this one would be repelled, this one would be attracted, and this one would be repelled. Remember, the arrow is always north. A compass always points in what direction. Very important here. Very, very important. Not north. It always points in the direction of the magnetic field. So if I have a little compass, a little compass in my room, it's going to point in the direction of the closest magnetic field, not in the magnetic field of the Earth, because the magnets in my room are much stronger. So maybe I'll be able to show you that sometime. Okay, let's take a look at the next page here. And let's head down to some flux lines between magnets. So draw the flux lines formed by the magnetics between the magnets for each diagram. So we're just going to start out with the magnet being like that, a solid bar magnet, and we know the flux lines are going to go in the direction of a compass. So we just put compasses in here. I'm sure you know this one by heart now. This compass would point this way, this compass would repel away. So there's no secret here, everybody know this by now. These flux lines would point this way. Okay, so now we're going to break the magnet. So we said this continues to be north. It creates a new pole south. This stays south. It creates a new pole north. Now we're going to draw the flux lines in between. So if you put a compass in here, what would the compass do? Compass would repel north, so the flux lines would go this way. And believe it or not, they're going to be really dense. So this would be a really strong magnetic field in there. Okay, letter C here. Same thing. Okay, let's put a compass in there. And what would the compass do? Ooh, can't you see that one? We'll put a compass in there. And so what would the compass do? The compass in here would point opposite. North repels north. So this would be the field lines. The flux lines would look like this. And we usually just have to draw the flux lines between the two magnets. Of course, the flux lines would continue into here, and they'd go out here, and so on. They would come in from there, and they would go out from there and connect. But we really care about this area right in here. What we say here is we get a super high flux density. This becomes very important later on when you want to make electricity. So when you have this super high flux density, super concentration of flux lines, you can actually use this for an alternator, as we'll see later on. Okay, what would a compass do here? So just put a compass in here. This compass would repel. This compass would also repel. So these flux lines will do this. And that's the kind of picture you get with these flux lines. You get a kind of a void in the middle here as they repel each other. And notice the arrow directions are very important. The same thing is going to happen here, except for now the compass would come in. So this compass would come in, this compass would come in, and this compass, would come in. So we have the same type of field there. So it's pretty simple. Just put the compass in and see what it would do. To check yourself, just draw a compass. What did the compass do? North repels north, north attracts south. And there you got it, okay? So let's go ahead here and see what we have on the last page here. Alright, so yeah, I really miss my horseshoe magnet. Can't really show it to you, but we have a horseshoe magnet in school. It's pretty cool. And what happens here with a horseshoe magnet is you get some really strong flux lines here. I have one that's super strong. It's from a ship in the Navy, and you wait till you see how strong it is. So the flux lines between here would be super, super, super concentrated. They're not supposed to cross. Sorry if I make them touch there. Just getting used to this pen. It doesn't really work that well. It's kind of cheap. So there you go. You get some super strong flux lines in there. Okay, so what happens when you stick a piece of wood in between the flux lines? Well, wood is what we call permeable. So the wood is not ferromagnetic. So the flux lines will just go right through the wood. I had a great demo of this in class, but hopefully you remind me, I'll show it to you. So the flux lines just go straight through, because that's the way a compass would point. The compass would point that way. Okay, iron on the other hand is ferromagnetic, which means it will actually create a tiny magnet here. So this becomes a south and this becomes a north. So some of you know, if you want to make a magnet out of something metal like a screwdriver or something, you just stick it in between in a magnetic field, and the flux lines will cause the magnetic domains in the material, and the metal in this case, to line up like a magnet. So what happens now is a compass in here. A compass would point across like this, and it would go right. You basically would have two strong flux lines in there. Okay, so the biggest misunderstanding is the Earth. The Earth's magnetic field and the geographic poles are showing. So draw the magnetic north pole. Well, if you put a compass here, we all know that a compass points to geographic north. A compass here will point to geographic north. No matter where you put a compass, it points to geographic north. Put a compass here, it points to geographic north. So that means, believe it or not, that the north geographic pole must be a magnetic south pole, and the south geographic pole is a magnetic north pole. They're the complete opposites, and not many people know that. So that's how a compass works. Remember now, the compass points in the direction of the magnetic field. In this case, it's the Earth's magnetic field. but easily in my room I have magnets that are stronger than Earth's magnetic field, and I can overwhelm them and show them that they draw in my direction of the compass will go in the direction of my magnets in my room. Actually, we're going to not do magnetic declination and inclination. That's for navigation. I'll have to show you this in school. It's way too complicated to explain without my demos, so we'll just leave this off for right now. Won't be on your quiz, guaranteed. Okay, and the very last thing, probably the most important thing about magnetism, is what can you do with it. So with magnets, with flux lines, you can actually create voltages. And this is really easy to demonstrate in school. So when we get back, remind me to show you this. Basically, we take a coil of wire, and I have a meter on the end. Then I would take a magnet, and I would plunge the magnet into the wire, or I can move the wire towards the magnet. It doesn't matter what you move here. When you do that, the needle will register a current. And this is the basis of a generator. So to produce voltage or induce voltage, you can move either the magnet or the wire, and you'll get a current to flow. So down here, like I said, you can move the coil towards the magnet, or you can move the magnet towards the coil, put it in there, and you'll see a current flow. It's pretty phenomenal, and this is the basis of all our generation of electricity. So basically, we just move coils of wire through magnetic fields, or vice versa, and we generate electricity, whether it's in your car, anything that has an alternator or a generator in it. But there is a trick. Okay, you have to be very careful. So when you have your magnetic field with all these strong flux lines, it's very important which way you move the actual object. So you have to actually move the object to be perpendicular to the flux lines. So what happens is they have to be perpendicular. So if I want to move a wire, I have to put the wire in here. I have to move this in, to, or out of the page, breaking the flux lines. You can move it at an angle and break the flux lines, but you don't get as much current. So to get the most current, you have to move the object perpendicular. So you have to break the flux lines perpendicular, and that'll generate a current in this wire. And then the wire can be connected to a battery or whatever you want to do, and you got yourself a beautiful circuit. And that's the basis of electrical generation. Remind me if you're interested. When we get back, I can show you this really simply. Okay, I think that's it for magnetism. Believe it or not, shortest unit we have. So in the future here, you'll see some homework coming your way. Please scan it, or actually print it first, scan it, and then send it back to me, and I'll correct it. And then I'll have some practice quiz questions for you, and then the final quiz. So thanks for listening. If you have any questions, you know where to find me.